Hi everyone. In this video, we will continue our discussion of measure. In particular, in this video, defining the Lebesgue measurable sets and what their Lebesgue measure ought to be. So in a slightly unusual way of doing things, we're actually going to start by defining what sets are Lebesgue measurable without telling you what the Lebesgue measure is. And then actually at the very end of this video, we'll actually say, given a Lebesgue measurable set, here's how we can find the Lebesgue measure of that set. So to begin, we want to define what it ought to mean for a set to be Lebesgue measurable. So we say that a set E is Lebesgue measurable if and only if, for every subset A of R, we have the following condition, and this is actually called the Carathéodory condition. So this condition says a set E is measurable if, for every set A, the outer measure of A is equal to the outer measure of A intersect E plus the outer measure of A intersect E complement. And if we take every set E that satisfies this condition, then we call that set of sets the set of all Lebesgue measurable sets, which we just denote by this script M. Okay. Now, before we proceed, let's actually take a moment to sort of look at this condition and think a little bit about what it actually entails. So, informally, one way to view this is to say that a set is measurable if it splits every other set into two pieces whose outer measures add correctly, right? So again, just to rewrite this condition, right, it's mu star of A is equal to mu star of A intersect E plus mu star of A intersect E complement, right? So this set E, right, I'm taking it for any set A, I'm taking and creating these two sets, A intersect E and A intersect E complement. So really what these sets are doing is it's taking a set A and it's splitting it into two pieces, the parts of A that are also in E and the parts of A that aren't in E. And what this is saying is a set is measurable if when you split every set A according to whether it's in E or not, the outer measures add in the correct way, right? So that the outer measure of A intersect E complement plus the outer measure of outer measure of A intersect E plus the outer measure of A intersect E complement adds up to just the outer measure of A. Okay, so one way to sort of, again, think about measurable sets is there's sets that split up other sets so that the outer measures add appropriately. Okay. Now, let's note a few things about this condition. So the first is that it's symmetric. So if E is measurable, then so is E complement. Now, why is that true? Well, imagine E is measurable, okay? And then I want to check this condition for E complement, okay? Well, that would just say I would want mu star of A to be equal to mu star of A intersect E complement plus mu star of A intersect E complement complement. Okay. But E complement complement, any set complement complement is just the set E. Okay. So this is mu star of A intersect E complement plus mu star of A intersect E, right? And I know that this holds because E was measurable. So again, because E was measurable, this is equal to this, but I can rewrite this E as E complement complement, and the fact that this equation holds tells me that E complement is measurable. So if E is measurable, so is E complement. Okay, that's a nice thing to have. You can also pretty quickly from this definition get that the empty set is measurable. So how would we check that? Well, if I want to know that the empty set is measurable, I need to look at mu star of A intersect the empty set plus mu star of A intersect the empty set complement. Okay. Well, A intersect the empty set, that's just the empty set. Okay. The empty set has outer measure 0. Plus, now let's see, what is this? Well, the empty set complement, that's all of R. A intersect all of R is just A. Okay. So here I get this is 0 plus mu star of A, which is, of course, just mu star of A. So notice, right, I've got this condition satisfied. I have mu star of A is equal to mu star of A intersect my set plus mu star of A intersect my set complement. Okay. So the empty set is measurable. Now, I could repeat this for the reals, but I could also recognize that the reals are the complement of the empty set, and the empty set is measurable, so the reals are measurable. Okay, so this is nice. Now, we will, in this video, prove this for some other kinds of sets. Let me make one observation, though. Okay. My goal is going to be in every case where I want to show something's measurable, I want to show that this condition holds. But let me note that one way of proving this, right, could be to try and prove that the left-hand side is less than or equal to the right-hand side, and that the left-hand side is greater than or equal to the right-hand side, right? You could split this up into proving two inequalities instead of just proving the equality. Okay. Well, one of those directions is trivially true. So notice that if I take my set A is equal to A intersect E union A intersect E complement, right? So you can see where I'm getting those pieces from, right? So my set A is equal to A intersect E union A intersect E complement. And in the last video, we showed that outer measure, it's not countably additive, but it's countably subadditive. So what did that mean? Well, that meant you could break up the outer measure over a union, but you got a less than or equal to. So the fact that, just use a different color here. So by countable subadditivity of the outer measure, mu of A must be, sorry, mu star of A must be less than or equal to mu star of A intersect E plus mu star of A intersect E complement. So you always get this for free. So if you want to show something is measurable, you really only need to show the inequality in the other direction. So to show E is measurable, it is sufficient to just show the other inequality. So to show that mu star of A is greater than or equal to mu star of A intersect E plus mu star of A intersect E complement. Okay, so this is just a nice sort of consequence of subadditivity, right? That really I don't have to show, I don't always have to do a lot of work to show one direction of this, right? I automatically get this direction of the inequality for free from subadditivity. I just have to work a little harder to get this piece. All right. Now, we want to look at proving that some other sets are measurable. So let's show actually that sets of outer measure 0 are always measurable. Okay. So again, the only tool we have at our disposal right now, right? If I want to show that something is measurable, I need to show that it satisfies that Carathéodory condition. Okay, um, so let A be an arbitrary subset of R. Okay, by subadditivity, right? So by subadditivity, we already know that we can prove that what we want in the inequality in one direction. So by subadditivity, mu star of A is less than or equal to mu star of A intersect E plus mu star of A intersect E complement. Okay, so now we just need to show the inequality working in the other direction. Okay, all right. So in order to do that, what we're really going to do is we're going to think about each of these pieces. Okay, so note that A intersect E. Right. So if I just look at A intersect E, that is going to be a subset of E. Right. Anytime you have two sets intersected, they are the intersection is a subset of either one of the sets. Okay. So what does that mean? Well, we have monotonicity of the outer measure. So that means that mu star of A intersect E has to be less than or equal to mu star of E. But remember here, we're assuming that our set has outer measure 0. Okay, so that actually means that the outer measure of this has to be equal to 0, but it turns out we don't even need that part of it, just that it's less than or equal to 0. Okay. Now, okay, that's nice. Let's look at this piece. Okay. So now note that A intersect E complement, that's a subset of A. And so again, applying monotonicity, mu star of A intersect E complement has to be less than or equal to mu star of A. Now, I don't know anything about mu star of A. A is an arbitrary set, okay? But now, if I just take these two inequalities and add them, right, what do I get? Hence, mu star of A intersect E plus mu star of A intersect E complement. Well, mu star of A intersect E, that's less than or equal to 0. Mu star of A intersect E complement, that's less than or equal to mu star of A. And 0 plus mu star of A is just mu star of A. And so now notice I have this same thing, but now the inequality is pointing in the other direction. Okay. And so therefore, mu star of A must be equal to mu star of A intersect E plus mu star of A intersect E complement. And so E must be measurable. So we write this. This is the same as writing E is measurable. E is in the collection of Lebesgue measurable sets. So again, I mean, notice here, what are we really doing? We're trying to prove this Carathéodory condition. Okay. And the way we do that is by proving an inequality in two directions. The first one we get for free from subadditivity. The second one we have to do a little set theory and use some properties about our set E in order to get that. But then we get the Carathéodory condition, and so our set E is Lebesgue measurable. Now, notice that as of yet, this doesn't tell us anything about what the Lebesgue measure is, right? We're just saying if your set has Lebesgue outer measure 0, then your set is Lebesgue measurable. Okay. Now, you probably would hope in the back of your mind that if it has Lebesgue outer measure 0, outer seems to suggest it's some sort of overestimate, right? So you would hope that if the overestimate of the measure gives you 0, then the actual measure should be 0, right? But we haven't proven that here. We've just proven that this set is Lebesgue measurable. All right. Let's look at one more example, just of working with a particular kind of set and using this Carathéodory condition. So let's now prove that if I take an interval of the form a to infinity, I want to prove that that's measurable. Okay. Now, here, right, if we sort of think about this for a minute, this is a little bit sort of maybe seems trickier because if I think about, again, I don't know exactly what Lebesgue measures, but the Lebesgue outer measure of this, right, is infinite, right? But again, notice is that we sort of feel like, I think the first time I ever saw this, it made me feel a little uncomfortable because I thought, oh, I've got to deal with something that its measures is infinite. But whether or not something is Lebesgue measurable has nothing to do with what its Lebesgue measure or Lebesgue outer measure is, right? So we shouldn't really be worried about that too much. It really comes down to just some set theory, right? Proving some things about set theory. So let's look at that example. So let's take, again, I'm going to take a set, an arbitrary subset of the reals. Okay. And I'm going to define a couple of other sets. So I'm going to define a set A1 to just be A intersect my interval here, okay? And A2 to be A intersect E complement. So really what I'm doing here is I'm just defining some things to make, I'm defining some things to give me some shorthand. I don't have to keep writing A intersect E and A intersect E complement. Okay, so I just want to define those things. Now, again, clearly, mu star of A is less than or equal to mu star of A intersect E, but that's what I'm calling A1, plus mu star of A intersect E complement, that's what I'm calling A2. And again, this just holds by subadditivity. I think my red markers are going. Yeah, I'm gonna retire them after this sentence. All right. All right. Red markers are expired. All right. So now we just need to prove the other direction, right? All right. Now note that if mu star of A, so this arbitrary set A, if it has infinite outer measure, I'm done. Why? Well, if mu star of A is equal to infinity, certainly that's greater than or equal to, or let me write it this way. So if mu star of A is equal to infinity, then infinity, which is mu star of A, well, that's greater than or equal to anything else I want to put over here. It's certainly greater than or equal to mu star of A1 plus mu star of A2, right? I mean, what could these possibly be that they would add up to something more than infinity? Nothing, right? And so If mu star of A is equal to infinity, we're done. Okay, because I'll get the other direction and I get the Carathéodory condition is satisfied. All right. So now what if it's not? Okay. Well, now consider the case where mu star of A is finite. Okay. Now remember, A is our arbitrary set that we're using for our Carathéodory condition. E, of course, E certainly has infinite outer measure. Okay. But this isn't about whether E has infinite outer measure or not. It's about whether this arbitrary set A we're working with has infinite outer measure or not. Okay. All right. Well, if this has finite outer measure, then what? Then there exists an open cover. And let me call the elements of those that open cover IN. So those are each of the IN are open intervals. And there exists an open cover IN with so uh, sorry, I've written this a bit backwards. Let me fix this. So I'm going to make a little interjection here. Then for any epsilon greater than 0, right? So for any epsilon you give me, I can find an open cover IN such that the sums of the lengths of all the intervals in my open cover minus mu star of A is less than epsilon. Why is that? Well, mu star of A, by definition, is what? It's the infimum over all open covers of the sums of the lengths of the open covers. So this is the infimum of all of these things. So I can certainly find one particular one that gets within epsilon of mu star of A. Okay. So for any epsilon you give me, I can find an open cover that satisfies this condition. Okay. All right. Now, if I rearrange this slightly, right, basically what I want to do is I want to just move the mu star of A to the other side. So I can rewrite this. I can rewrite this in this way. All right, and now I want to use this. So now I'm going to define IN prime. So my IN primes are going to be, I'm going to take my INs and I'm going to intersect them with E, or sorry, yeah, with E, okay, with my interval here. And let IN double prime be my INs intersected with E complement. Okay, so now what I'm doing is I'm taking these INs are an open cover of A. I want to understand how A splits with respect to E and E complement. Okay, so what I'm going to do is I'm going to sort of take as a proxy for A, I'm going to take its open cover, right? And I'm going to see how this open cover splits with respect to E and E complement. Okay. Now, one thing to note here is that IN is an interval. It's an open interval. E is an interval. And so IN prime must also be an interval. Where we allow here that, I mean, it's possible that it's the empty set, which is sort of a degenerate interval. It's possible that it's the whole space, right? But This is in prime is still an interval, and in double prime is still an interval because in is an interval, and E complement will also be an interval. It'll be the interval from minus infinity to A closed at A. Okay. So these are both intervals, which is important. So then since in prime and in double prime are intervals, if I look at the length of an in, well, that does partition nicely. That's the length of in prime plus the length of in double prime. Okay. Again, in is an interval. It splits with respect to this. The lengths are additive here. Okay, they have this countable additivity property. But then again, because these are intervals, the length is equal to their outer measure. Okay, so I also get that the length of in is equal to the outer measure of in prime plus the outer measure of in double prime. All right. So now what can we say? Let me give myself some more room. Do a little erasing here. All right. So if I look at mu star of A1 plus mu star of A2, okay. So let's see what's going to happen here. So if I think about A1, what is A1? A1 is A intersect E, okay? But the in primes form an open cover of A1, right? So maybe just to keep track of it, right? We had A1, this was A intersect E. And now we have these in primes. They are in intersect E. But remember, the ins formed an open cover for A. So these in primes must form an open cover for A1 because you basically just taken everything and intersected it with E. Okay. So what does that tell me? Well, that tells me that since the in primes are an open cover for A1, mu star of A1 must be less than or equal to the sums of the lengths of the in primes. And similarly, we have A2. A2 was A intersect E complement. In double prime was in intersect E complement. Well, again, the INs are an open cover for A, so the IN double primes have to be an open cover for A2. So the outer measure of A2 must be less than or equal to the sums of the lengths of the IN double primes. But again here, these are intervals. So these are equal to their outer measure. Sorry, that's true, but we actually don't need that. Yeah. We can actually just combine these sums, lengths of the in primes plus the lengths of the ins. And again, or the in double primes. These are additive. So these are lengths of the ins. But remember, we chose our open cover so that this sum was less than mu star of A plus epsilon. Okay, and we could do this for any epsilon. So what I have here is that mu star of A1 plus mu star of A2 is strictly less than mu star of A plus epsilon. And that works for any epsilon. I can do this. Okay. So taking a limit as epsilon goes to 0, we get that mu star of A1 plus mu star of A2 is less than or equal to mu star of A. And that's the other direction we needed, right? And so we can conclude all this, right, by saying hence mu star of A is equal to mu star of A1 plus mu star of A2. And so the set E, which here was A to infinity, is measurable. Okay. All right. So we get that this interval is measurable. Nice. Okay. Now, of course, we've only really shown a couple of things. Right? We really only here can say that a few things are measurable, right? So far, we've got the empty set. We've got all of R. That's not very interesting. I think we'd actually be in trouble if we'd be in really big trouble, right, if those things weren't measurable. We've now gotten any set of outer measure 0 is measurable. And now we have that this one particular type of interval is measurable. Now, if you think back to some of the other stuff we talked about, like we'd like to maybe be able to say that like all intervals are measurable. That seems like at least open intervals, right? If you think about outer measure, right? Outer measure is defined in terms of these open covers. I mean, you don't necessarily just assume anything works in math, but you'd sort of hope that, like the standard open interval AB would be measurable. So the question becomes, how can we maybe extend some of this without having to go through case by case and prove that everything is measurable? How might we extend some of this? Okay, well, let's think about that. So let's take the fact that we know that the interval A to infinity is measurable. What can we say about the following things? Well, the first, what if we just change, like, instead of this being closed or being open at A, what if we changed it to closed? Well, what I encourage you to do is go back and look at the proof that the open interval A to infinity is measurable. And ask yourself, at any point did we use the fact that this was open? No, the only facts we really used were that this was an interval. Okay. And this is also an interval. Okay. So this will actually work in exactly the same way. Now, we did use the fact here again that this is infinite, like in showing that, for example, in intersect E is just a single interval. You really do use the fact that this is an infinite half interval, or like an infinite ray here. So we do use that, but we don't ever use the fact that this is open at A. So actually that same proof will work exactly the same. Okay, but then you get to something like the open interval AB, and then you have to start asking yourself, well, what could I do? Like, I know that if a set is measurable, its complement is measurable, right? So I could wonder, well, could I write this as the complement of something that looks like this? And you realize pretty quickly that the complement of either one of these things is another like infinite ray, essentially. So that's not really going to work. But one of the things you start to realize is, well, okay, what about so if the interval, what if I take this interval? If I take b, that's measurable. Okay, and that implies that minus infinity to b is measurable. Okay. And this is measurable plus the fact that uh, a to infinity is measurable. Well, could I conclude that if I take like the intersection of these, right? Right, this would be equal to AB. Could I conclude, I'm going to write a question mark there, could I conclude that this is measurable because it's the intersection of two measurable sets? Well, and even if you didn't want to do this with, if you did not want to do this with, with intersections, you can also do this with unions and complements, right? So we could actually follow through this in a similar way. So you can make a similar argument. I'm not going to maybe spell this out quite as much, but you could argue that if I look at a to infinity complement, okay, and I union with that b to infinity. So this is measurable. We already proved that. Its complement, therefore, has to be measurable. This is measurable, right? We said we can just use the same proof for that. And then if I take the complement of this whole thing, okay, then that will give me AB. If I knew that the union of two measurable sets was measurable, then I could say that this has to be measurable, and then its complement has to be measurable, so this thing has to be measurable. So what we start to realize is it'd be really nice. We can already say things about the complement of a set. Complement of a measurable set is measurable. We'd really like to say something about unions and measurability. And then if we could say something about unions and complements, then we could certainly say something about intersections. De Morgan's laws allow us to rewrite intersections as unions of complements. Okay, so we actually from just this alone, right, these two things alone, would be able to get all the other intervals being forced to be measurable if we knew that the union of two measurable sets had to be measurable. Okay. So the next question becomes, well, is that true? And the answer is yes. Okay. The union of two measurable sets is indeed measurable. Now, we are not going to prove this theorem in the video. It's theorem 3.7 on page 131 of the text. You're welcome to go look at it. I would encourage you to go look at it and see if you can follow it through. I will say that the proof is very heavy on set theory, right? It's very reliant upon rewriting these things as rewriting certain sets as certain unions and intersections of other sets. So you spend a lot of time doing set theory, but the result does fall out. So you show that if the Carotheodoric condition is satisfied for E1 and for E2, then you can show it also has to be satisfied for E1 union E2. So it's not sort of a very conceptually difficult proof, but there's just a lot of set theory, a lot of sort of technical calculations going on. Okay. So from this alone, it immediately follows that all intervals have to be that all intervals must be measurable. Okay, but we can actually take this a little bit further. In fact, it's not just any two measurable sets, their union has to be measurable. If you take a countable sequence of measurable sets, then their countable union must also be measurable. Okay. Now, on the one hand, you might say, okay, fine, maybe that doesn't seem as interesting, right? So you can see that it's a technically more impressive result because you're dealing with a countable union there, but you might sort of think it's not that valuable. However, and what I want to conclude this video with, we're not going to prove this result either. It's theorem 3.8. Again, the proof is in the book. It's a lot of set theory, and I'm not a set theorist. I'm an analyst. The proofs are good practice for set theory, but I don't necessarily find them particularly useful in terms of learning more analysis. So you're encouraged to look on that. Again, that's theorem 3.8 in the book. That spans page 131 and 131 and 132. But what I do want to talk about are the consequences of this. So, an immediate consequence is that the collection of all measurable sets forms a sigma algebra, right? Because now we've shown, just from the definition, you can see that the complement of a measurable set is measurable. And now we know that the countable union of measurable sets is measurable. A collection of sets which is closed under countable unions and complements is what we call a sigma algebra. So the collection of measurable sets forms a sigma algebra. This says it has a really nice structure. Okay. But now we can even take this another step further. That sigma algebra, the set of all measurable sets, what does it contain? We said, well, it contains all the open intervals, right? Just from the finite unions, right, you can get all the open intervals. So the set of all measurable sets is a sigma algebra, which contains all the open intervals. The Borel sets, what are they? It's the smallest sigma algebra containing all the measurable sets. So you have the smallest sigma algebra that contains all the open intervals, and another sigma algebra which contains all the open intervals. Certainly the Borel sets, must be a subset of the measurable sets. Now, a much harder question to answer is, are these the same? Okay. And it turns out that the answer is no. So the Borel sets are a subset, but are not equal to the measurable sets. The construction of a non-measurable Borel set is possible. But it's outside the scope of what we want to cover. It's a very technical sort of construction. The book actually points you to a reference. If you're interested in looking at such a construction, points you there. So I don't want to spend time going through that, but there are measurable sets that are not Borel sets. Okay. Now, the other sort of interesting question, though, that then pops up is, so we know that the measurable sets, it contains more than just the Borel sets. But if you remember back when we were first talking about Borel sets, we said, the Borel set sort of lived between the set of all open intervals and the power set of R, the set of all subsets of R. Okay, so the question then becomes, well, maybe the set of all measurable sets is every set. Okay, so we certainly now know we know that the Borel sets are a strict subset of measurable sets. But another question would be, are the measurable sets, right? Certainly they're a subset of the power set of R, but are these equal? Okay. The answer to that is also no. Okay. And in a video coming up, we will construct a subset of the real numbers which is not measurable. This is the so-called, or the particular example we'll use is a so-called Vitali set. Okay. So you actually end up with this nice sort of hierarchy. You have the Borel sets. They are a strict subset of the measurable sets, which are a strict subset of the power set of R. Now, to conclude, we've been talking about what it means for a set to be Lebesgue measurable, but we haven't said what the measure is. The Lebesgue measure, it's just the restriction of the outer measure mu to the measurable sets. So said another way, if you have a set that's measurable, its Lebesgue measure is just its outer measure. Okay. If you have a set that's not measurable, then we're not going to talk about its Lebesgue measure. Okay. Now, this might seem a little strange. Like you might wonder why do this, right? Why not just work with outer measure? Well, essentially, the things that are every subset of R is outer measurable, right? You can compute an outer measure for any subset of R. Okay. But the ones that don't satisfy the Carathéodory condition, they're sort of bad in a way. Okay, they're bad in the sense that all those things on the wish list. Remember, for number 3 on that wish list, we wanted countable additivity, but for Lebesgue outer measure, we had to settle for countable sub-additivity. It turns out that if we restrict ourselves only to the measurable sets, the ones that satisfy that Carathéodory condition, then we will be able to recover countable additivity. Okay, so in some ways, these are the Lebesgue measurable sets are the subsets of R where the outer measure is well behaved. Okay, and then when the outer measure is well behaved, we just call that the measure, the Lebesgue measure of this set. Okay, so for example, we proved that an immediate consequence of this, right? We proved that if the outer measure of a set is 0, right, that implied that E was measurable. And now this definition tells us that the measure of E, the Lebesgue measure, it's equal to the outer measure, which is 0. Okay. Similarly, we showed that the outer measure, the outer measure of this interval A to infinity, that has to be infinite. Okay. We showed earlier, this isn't an implication, but rather combine this with the fact that we showed earlier that this interval is measurable. Well, what does that imply? That implies that the Lebesgue measure of the interval from A to infinity is infinite. So again, now you just have this definition that says, oh, for these nice sets, these Lebesgue measurable sets, the Lebesgue measure is just the outer measure. All right. Excuse me. We will conclude this video here. In the next videos, we'll be looking at both the construction of a non-measurable set, as well as some properties of Lebesgue measure. So these are, again, another way to think about these are properties of outer measure when you are only dealing with Lebesgue measurable sets, right? So we will look at those coming up.